Hello students, welcome back. Let us resume our discussion in Euclidean algorithm. Here's Euclidean algorithm. We begin with an initial pair A and B, where A is greater than B. If they're the same, then there's nothing to do. We can simply take the common number as a GCD. So A is greater than B in general, without loss of generality, and apply this division algorithm. We get even smaller integer r, and then GCD of those two gets down to GCD of these two. And then if I do this again, I'm going to get another one, which got down to even smaller pair. Another one. And so on and so forth. Repeat it many, many times. And eventually, you're going to get down to 0, the divisibility. And this one here is the GCD. That entire thing comes from the repeated application of this theorem, which we proved last time. And then we already went through a couple of exercise problems to find out the GCD through Euclidean algorithm. Here's one problem, and here's another problem. Remember those? Okay, let's go back to this, the first problem. And the original problem goes like this. Find the GCD, which we just did, and then express it as a linear combination of this. Let's focus upon the second half of the problem. So, we found it out. So this tells me that 2 can be written as a linear combination, 662x plus 414y. For some integers x and y, we know that. But here's a big problem. What are these x and y? What if we want to find it out? Find these out. Well, that's what we have to now. And we can use the Euclidean algorithm, this computation, and we can backtrace to find out. Now, one more thing. When we did this division algorithm and Euclidean algorithm to put together everything and getting the GCD, the quotient did not contribute. The dividend and divisor was reduced to divisor and remainder, and then the divisor and remainder, and the divisor and remainder, divisor and remainder until you hit 0, right? The quotient did not do a thing. Not anymore. This time, quotient will work really hard for you. And then I'll show you that. So, goal is to get x and y like this, all right? Okay, let's backtrace this problem. From here, I get 2, the GCD, 2 is 166 minus quotient 2 times 82. By backtracing, is that clear from here? So this one, we don't really need it. So from that one, is that clear? Okay, now 82 is smaller of the two. And here to this 82, which I'm highlighting in blue, we're going to apply the next line. 82 can be expressed as 248 minus the quotient times the divisor. So this entire thing can be rewritten as 166 was there before minus 2, which was there before, and that's 248 minus the quotient 1 times 166. This one, let me highlight in blue. That's from this second line. First line will get at where we started, and second line highlighted in blue gave me this. Okay, a little bit of simplification is in order. 166. 2 times 1, so that's positive 2, so 3 times 166 minus 2 times 248. That's what we have. So far so good. Now which is smaller? 166 is smaller. I just highlighted in green. And that's where I'm going to apply the previous line. Remember, I'm backtracing this problem. And the green line. So this is 3 was there before. And then, let me copy and paste all these. So all those are there before. And this 166 can be rewritten as 414 minus 1 times 248. Thanks to the line above. You see, we are backtracing this problem. Started from here, and then blue, green, and then we didn't use this one yet. Okay, some further simplification is in order. 434, so 3 times 414, and then 3 times 1, 83, and then we have 85 to 48. Did I do this right? Please check. Now, which is smaller? 248 is smaller, as I just highlighted in purple, and that's where I'm going to use the first line. Again, I'm backtracing the problem. Black, blue, green, and then purple. That's where we are right now. So 3 times 414, all right, minus 5. And then 248 is actually 662 minus the quotient 1 times 414. And let's use purple here. We're almost there. Everything here is written in terms of 414 and 662. So if you simplify, you're going to get the desired linear combination. 3 and then negative positive 5. So 8, 414, and minus 5, 662. Oh, is this right? 8 times 414 minus 5 times 662. Yes, it is true. So we successfully found out Bezout's linear combination expression of 2, the GCD. X value is 8, Y value is negative 5. I think I said backward. Oh, no, I said it right. X value is 8, Y value is negative 5 if I write like this. The answer key, Euclidean algorithm like this, and then we are backtracing each. So from here, and then 82 we rewrite. And then that results in this simplification. And then which is smaller? 166. That's where we're going to apply the line before, green. So this green, 166, you can rewrite like this. And then simplify. Now which is smaller? 248, that's smaller. Highlighting in purple. Something's not right. This is where we started, excuse me. And this is blue, and this is green. Sorry about that. And this one is not that important. Just checking. So, okay, this is purple. Yeah, that's 248. Flip it over and we get 662 minus 1 times 248. And then simplify. That leads to the final conclusion. Let's see, you think you can do this again? For the next problem, we did this. All right, we found out the GCD. Now let's backtrace that to find out the linear combination expression. Okay, let's begin. So this one is just checking process, so that's not really necessary. We start from 63. And 63 is 189 minus 126. That's the starting point. And then let's apply the second line, I'm highlighting in blue, to this 126. So that 126 is 693 minus 3 times 189 because of this blue line. And some simplification is in order. Alright, which is smaller, 693 or 189? 189 is smaller. Highlight that in red, and then let's use this red line. 189 can be rewritten as this. 882 minus quotient times 693. And then simplify, we get the desired linear combination expression by this way. So 63, the GCD, is 4 times 882 plus 85 times 693. Okay. Starting black, 63 is the dividend minus quotient time divisor. Yes, this time quotients do contribute. And then this 126, use a previous line to re-express. The dividend minus quotient times the divisor, that's blue. Yes, quotients this time do contribute. And then simplify. Okay, 189. We used the previous line, the dividend minus quotient time divisor, yeah, here again, and then simplify. All right, they can go on several more steps if necessary. Eventually, we get x and y. So we went through all those aspects of Euclidean algorithm. First, how to find the GCD. Second, how to prove Euclidean algorithm theorem. And finally, how to get Bezout's linear combination expression. The third application is the most important, and they will most definitely show up in exams.